All right, hello everybody. So today we're going to continue our conversation around distributed transaction and more prominently in the context of this exciting and vibrant emerging area, which is known as also blockchain. Last time we kind of stopped at this point. We talked about what is the blockchain. We talked about sort of the overall aim and the overall intention behind developing a decentralized and a democratic platform. And a simple representation of the blockchain, as we covered last time, is basically just a chain of block. And every block also internally maintains a hash of previous block. And the hash of the previous block is part of the puzzle that needs to be solved, for example, for block B2. So to solve this correct puzzle for block B2, the hash of its previous block B1 also is included. So this ensures that solving the puzzle for a second block, it can only be started once the first block is finalized. And that ensures a fair starting point for all participants. And of course, the reason that we have these puzzle, it makes the chain prohibitively very expensive or nearly impossible to fake after, for example, chain has been developed for some time now. In order to go and reverse the history, you need enormous computational power to do so. And the different threshold, you probably need at least 30% of the overall computational power in order to be able to reverse the history. And so that makes the blockchain resilient, fundamentally resilient, because of the proof of work that it gets stamped on every block that gets created. We talked about the economy aspect of it. I'm not going to go over those parts again, but in sort of permissionless and the Bitcoin style of blockchain that relies on proof of work, it is possible that forks gets created, and the reason for the fork, it could just be two different participants solving the puzzle at the same time. And eventually, the network will choose one of these choose one of these blocks and start adding more blocks to it. For example, here, there was a fork at B2, but the B3 and B4 end up being added to the B2, not to the B2 prime. So eventually B2 prime gets dropped. And so the basic model is that you want to add your block to the longest chain. And that then this property ensures that the longest chain will survive. And this property also ensures that in order to actually get the reward and in order to get the incentive, you better be on the longest chain. So naturally, all the participants will only focus on the longest chain. So that's the basic of the permissionless. And what are the, again, elements of this? We have a ledger, which is an append-only sequence of transaction, as a journal or a log, and that's very similar actually to the ELSTOR. ELSTOR, the base pages are simply an append-only log and sequence of transaction. So essentially, this ledger is identical to base pages that we have in ELSTOR. Of course, we also have the notion of tail pages, which is also another append-only journal, but periodically there is a consolidation between the tail and the base. But in blockchain, in this type of ledger, we're just having this sequential log, and there is no other simply any kind of new transaction that comes, it simply gets appended to this log, and this log is the representation of all the transaction that has been executed so far. And you may also have, in addition to the logs, also this is the case in databases, you have the log, which is your ground truth. Given the log, you know exactly, for example, if you were to replay the log at any time, you can reconstruct your database in a more efficient form. And so you also, in addition to the log, you may have a database state stored in tables and in indices and all of that, but that's kind of orthogonal or that's complementary. It's not essential to the chain itself. To the chain is, as far as the chain concerns, is an append-only ledger of sequence of transaction. It's just essentially our database log. And now whether each participant also want to maintain a more efficient representation of that log, which will be, for example, LSTOR would be a more efficient representation of the log, but that's something that's seen as sort of an optimization of how to answer queries more efficiently. But as far as the correctness and the correctness is concerned, or as far as the chain is concerned, the only thing that needs to be maintained, a log of transaction, which is essentially, in our database term, is our database log. And we have resiliency and availability. And the reason we have this resiliency availability is because we have the replication. As we talked about it, we have this decentralization, is that every participant, every entity will have their own copy of the log. So if the minority of these logs are unavailable, still the system can progress. And why is it tamper-proof? So there are two ways of being tamper-proof. One is that since we have many copies of it, as long as the majority of the replica are assumed to be good, the majority of replica are good and are available, we can, based on what the majority says, we can determine what the correct version of this log is, what is the correct chain. And so as long as the majorities are available, then you can't really tamper with the state of the log. Of course, in the permissionless, the mere fact of creation of every block, it also corresponds to a heavily computational puzzle solving. It also adds a second level of resiliency. Not only that, the majority need to agree upon or what the truth, or not the truth, but what the current state of the log is, what is factual. Not only the majority need to agree upon, but if you were to reconstruct and to create an alternative version of the world, it will be extremely costly because you need to solve all those puzzles again from scratch. So that's you could say there's another level of tamper-proof, or there's another level of resiliency that is added in the permissionless setting. But at the end of the day, blockchains are nothing but a distributed, fully replicated system. Or in other words, there is nothing but a distributed way of maintaining this log. You have a set of participants, each have a copy of the log, and as long as the majority agree on what the value of the log is, as long as the majority agree on what is appended to the log, then you can assess the correctness of the action of reading the log and the action of appending to this log. So in those very basic terms. So what are the components of the blockchain? So we typically define a replica. And so each replica have a copy of the log. Replicas are the participants that are participating in maintaining this ledger. So in this picture, we have R1, R2, R3, and R4. So we have 4 replicas. Each will have a copy of the ledger. Each will have the copy of the log. And again, log is nothing but just a sequence of transaction. So a client with a new transaction, so client comes, submits a new transaction, and there is a phase of an agreement. There's a consensus happening among all these replicas to say, okay, because there could be many clients that are submitting transaction, or there could be the same client submitting many transactions. So if I am constructing a log, and log by definition is a sequence of transaction. So by the definition, the log has a linear order. So now if I have multiple participants and they each maintaining their own log, in order to make sure that there is consistency among these logs, meaning these logs are essentially identical, then you have to ensure that everybody agrees upon the transaction that is being added to the log. And so that's important. So everybody, if the client is adding a transaction, and everybody will have to take the same transaction and everybody add that transaction in the exact same order to their log. And that's the main problem of consensus, to be able to ensure that everybody adding transaction in exactly same order, which is also called as linearizability. In serializability that we've been talking so far, which is sort of the cornerstone of correctness in the traditional databases, is that all it says is that it talks about the serial order in terms of the only caring about the non-conflicting. So you could have any kind of order on non-conflicting operations, but on the conflicting operation of the conflicting transaction, you need to have consistent ordering. So it does create an order, but that order is more relaxed because it doesn't say anything about things that are non-conflicting. For example, if T1, T2, and T1 and T2 are non-conflicting, if the system was serializable, it was okay if replica R1 had T2 followed by T1 and R3 had T1 followed by T2. That's okay on the serializability. But when we talk in the space of the blockchain and we talk about linearizability, there is even a stronger condition on that. Is that everybody need to see the exact same order. So that's the linearizability aspect, which is stronger than serializability. And it also considers each transaction to be done as a single action. So the actions of a single transaction cannot be split apart. It's just it's not a divisible unit. It's a single unit, all or nothing. It cannot be broken into smaller pieces. So that's another thing about linearizability, is that same order and there's no interleaving is possible, and everybody needs to observe the exact same order. And that's what the agreement is about. Everybody add the exact same transaction in the same order to their log, and the consensus is to ensure that that is done correctly. So again, T would eventually get added to the ledger, but everybody, or at least the majority of the replica, or the honest replica, will add the T in the same position to their log. And of course, there's cryptography that it used. For example, the client will make sure that the transaction that is submitted is signed, so you can verify that this was really sent by the client, and there was no malicious entity who kind of intercept, or a malicious entity on the behalf of the client says, okay, the client wants this particular action. So again, there's a lot of signature that, or cryptography and private public key that are used internally to ensure the authenticity of the messages that are being received. Of course, it is possible that the parties, for example, there are malicious entity, including the client or some of these replicas, that they are colluding with one another, and they may pretend, so they're colluding. So that means they do have access to each other's private key. So again, all of these protocols need to be able to sustain any type of fault arising from collusion among malicious entity. So let me just kind of pause here. Any questions on the sort of the setup of the consensus, and how do these blockchains or these distributed replicated systems are set up?
I have one question. I've seen a couple, I guess, blockchain technologies that don't look for total agreement across all nodes, but just partial agreement. Is that kind of one of the dangers, I guess, that you could have a large block of people colluding to kind of distort what's happening? Or
so that's an excellent question. No, technically they're not. So it's not about the so the system still needs to be safe under partial agreement, and the partial agreement, it's actually then becomes serializability, and in fact becomes sharding. So it's, instead of everybody maintaining the entire ledger, you kind of partition the data. So participant, for example, these participant is like partition databases. So these sort of participant only maintain the ledger data for North America. These only maintain the ledger for Europe or Africa or Australia. So there is a partitioning happening. And now, if there is a partitioning, and if your transaction doesn't necessarily touch every single data from all region, then you can only direct that transaction, for example, to North America and Africa, if that's what the transaction is hitting. And so the other ledgers could just simply be unaware of it. And you can further add serializability to say serializability to the mix as well, as opposed to having a linearizable order, which is everybody see transaction exact same order. You start saying, okay, can I make this serializable? Is that it's okay if R1 and R2 don't see exact same order if those transactions are non-conflicting. So that would be another relaxation. So there's a lot of interesting work on sharding, so sharded blockchain. In fact, in our group, we've been developing several different sharding protocol over the last year or so. So some of our decent sharding protocol is it can scale nearly 1 million transactions per second, over 500 replicas globally, 15 countries, and so at a very large scale. And Bitcoin, for example, does 7 transactions per second, or Ethereum does just around a dozen or so transactions per second. So these shardings are really powerful, and of course they're going to be serializable. They're not going to be you can't do linearizability with sharding. I mean, you could, but you kind of defeat the purpose. So Bitcoin, a permissionless blockchain, or Ethereum, and the key distinction between them is the membership problem. So in permissionless, anyone can participate. There is, or in other words, there is no notion of identity. And since there is no notion of an identity, then, and we still want to reach a form of an agreement because we want to agree on what the ledger looks like, since there is a notion of an agreement, then in order to reach an agreement, there needs to be some voting. So agreement is done in a democratic way with a voting protocol. But if anybody can join, and you don't have to reveal who you are to join the system, and you still need to vote, one clever way of dealing with that is you allow people to vote as long as they can solve a puzzle. So the barrier to vote is to do an expensive computation. In a normal election, the barrier to vote is to have a social security and identity. So in a permissionless setting, it's decentralized membership, or it's an open membership. Anyone can participate. There is no government registration. There's no single centralized authority that issues identity. So anyone can join. But then in order, anyone can join, but in order to make sure that whoever just joining cannot disrupt the system by adding malicious blocks or by trying to disturb the chain, is that you really have to solve this super expensive puzzle, a random puzzle. And so that becomes the barrier. And this also, we say, okay, now I need to participate. I have to spend so much money and so much energy to solve this puzzle. What's the point? Well, the incentive is there's also a reward. And that reward is proportional to the perception of the value of that cryptocurrency. So right now the Bitcoin is perceived very valuable by the community. So its price, I don't know, it's maybe $40,000 per Bitcoin. It's going up and down, fluctuates a lot. So that's the price of the Bitcoin. And that because there is a perception for it that this is a valuable cryptocurrency and this is a valuable economy. And so you pay so there's an entrance cost, there's a vote of the vote. Every time you want to vote and to get the block and sort of be able to be the winner of the block, you have to solve the puzzle. You don't have to show who you are. You don't have to demonstrate your identity. You just need to have computational power. So that's permissionless. The alternative, which we kind of focus on, and in my research group at UC Davis is the permission setting. And the permission setting is that the participants are known, or in other words, it's a closed membership. Another word is that there's an identity. You cannot, so in order to participate, you need to have an identity. You need to have a registration. And it doesn't mean that you are necessarily an honest person or an honest entity or an honest participant. It just basically says you have registration. So your identity is, you have an identity. And since you have an identity, then we can have an election. So now we have to make sure that our election and our voting protocol in presence of non-honest participant can still reach correct agreement, and whatever agreement is reached can be remembered forever. So we're solving the voting problem or the agreement problem in a reliable way as well too. And again, different attack model is it's been tolerated, and again, crypto and which is could be different from the cryptocurrency. And the reason they could be different from the cryptocurrency is because there is, for example, the concept of selfish mining is that there is a selfish mining, and selfish mining basically says, when I solve a puzzle, I don't tell everybody else what the result of the puzzle was. And the reason I do that, because I can start on the second puzzle. I can work on a second block, and it allows me to get ahead of everybody else. So it gives me starting point advantage. So for example, that's a type of attack model that is very unique to Bitcoin or any cryptocurrency that is not relevant to non-crypto type of consensus. One thing about permissionless is that because of being so computational heavy, they're very expensive. The transaction throughput is very low. And also the settlement time, it could be about an hour. So the latency of a transaction to be executed, it could be about an hour. Versus in the permissioned setting, we could get sub-second or second or few second latency, or at least that would be the aim of, that would be the aim. So again, two type of blockchain, the permissionless or the public one, that name's used interchangeably, or permission blockchain or private blockchain, which there is identity, and we use more like a classical type of reliable election protocol or voting protocol. Any questions? So what is it that we already have? What kind of technology? I mean, the problem of consensus or the problem of agreement is not a new problem. It's something that has been around for probably at least 40 years. In distributed computing, of course, blockchain and Bitcoin, it's something that came about around 2008. But distributed computing or distributed system, it's a much older area in comparison. So traditional consensus protocol, as one is called PBFT, Practical Byzantine Fault Tolerant, one is Paxos, and of course proof of work or proof of stake is on the permissionless side. Those are also variant of the same problem. PBFT can handle Byzantine fault, Paxos can only handle crash tolerant, proof of work, which is again you show a proof of that you did some work, and so that's can handle Byzantine. Proof of stake is instead of you put a lot of computational power to create a block, you put stake. You put money on the line, and then essentially the more stake that you have, the more chances of be able to win a block, and essentially in a way, the more stake you have, the more interest you get over the long term. So proof of stake is an alternative, more efficient way of doing consensus in a permissionless setting in place of proof of work. But what does all of these protocols have? So formally, there needs to be a termination, meaning each non-faulty replica decides on a transaction, and there needs to be non-divergence. If non-replica decide on the same transaction. So basically, termination is there's progress. Eventually, there needs to be a transaction that is added to the ledger. Non-divergence, meaning that the non-faulty replica, when they add transaction to the ledger, it's the same transaction. So termination, it's progress. Non-divergence is that correctness. So there is a safety condition. So the same transactions are being added to the ledger, to all the ledgers, or all the copies of the ledger. And of course, you could have trivially have a correctness criteria of never adding any transactions. If nobody's ever added any transaction, well, that's correct because there's no divergence, but also nothing is happening. Another way of kind of saying the non-divergence is that nothing bad happens. Another way of saying termination is that eventually something good happens. So safety, nothing bad happens. Termination or liveness, something good eventually will happen. So again, another way of describing this, liveness versus safety. Liveness, there is eventually a progress. Safety, there is agreement, there's consistency among the replicas. There's other formal definitions you could add. Validity. So when a transaction added to the ledger is actually a real transaction that was requested by a client, and that can be determined by the client having signed the transaction. So the authenticity of the transaction can be verified. There's also a notion of response, that once the transaction was actually added to the ledger, the client is also gets informed that the transaction was committed and executed. There's also a notion of service, is that you allow every client to eventually request the transaction, and eventually that transaction will be added. So there is a notion of services also can be discussed. But determination and non-divergence, those are the number one aspect of the correctness criteria of the any consensus: termination, liveness, non-divergence, safety. So client, pictorially, clients have a transaction T, it sends it to these replicas, a consensus happens, client gets informed, or the transaction gets executed, and the outcome of it gets informed to the client. So again, in consensus, we operate in the notion of rounds. And so in every round, a client submits a transaction. That transaction is added to that P round or that row round, and then it's executed, and then the client gets informed. And since every round one transaction gets added to the ledger, it's essentially added in a linear order, which is called that linearizable order. And also there's an assumption here that the execution of the transaction is deterministic. And the reason that is also required because each replica agrees on on every sequence number. So let me also actually define the sequence number too. So another way of saying around is that every transaction gets sequenced. So first transaction sequence number 1, second transaction sequence number 2. So there's a monotonically increasing sequence number. Or in other words, sequence number can be seen as an advancement of time. First transaction, everybody agreed was at time 1 p.m. Second transaction, everybody agreed was at time 1:10. Third transaction, everybody agreed was at time 2:50. And monotonically increasing time, a monotonically increasing sequence number, a monotonically increasing round number that is associated to each transaction. And so there's that linearizable, there's that linear order of the growth of the log based on that sequence number. And everybody agrees on that sequence number, or everybody agrees on the time that transaction was accepted. And since every replica will independently, once determine the sequence number of the transaction, goes ahead and execute that transaction and produce the outcome. If the execution is non-deterministic, even if the transaction was executed at the particular sequence number, if the execution is non-deterministic, meaning that, for example, a dice was flipped, then the outcome will not be the same. So although the log is consistent, the actual state of the data, there will be inconsistency. So therefore, most of these consensus system actually does assume that the execution itself is deterministic, and the execution is deterministic. So therefore, the you need to agree upon on the order in which the transaction is added to the log. There is need to be agreement on the sequence number attached to the transaction, and then once it's placed on the log, then independently that transaction can be executed and its output or its result can be informed. It can be sent to the client, and the client can be informed of it. And there is an assumption that the execution is deterministic. Otherwise, even if every replica adds a transaction T to the same sequence number, if the execution is non-deterministic, the client could get n different answer. So as far as the client is concerned, something is not right. So it doesn't know. One of them says your transaction, the result of your new balance is $5. One says your new balance is $7. One says your new balance is $20. So as far as the client's concerned, it doesn't make sense. So it would complain saying that maybe something malicious is happening. Any questions? So in a kind of the broader thing, and this might be, you may come across this, it's a famous theorem. It started with a conjecture in early 2000, and then it was later proven. It's called the CAP theorem, and it's a really broad characterization of distributed system in general. It consists of three parts: consistency, availability, partitioning. Consistency is essentially everybody have the exact same copy of the data. Availability, that the system can continue, operate always, there's always live, there's a liveness. So consistency is the safety, and then liveness is the availability, and the partitioning is that even if there is network disturbance, for example, half of the network gets partitioned, then the system can continue the progress. And what the CAP theorem, the conjecture was that only 2 out of 3 is ever possible. Kind of thinking about it, why is that the case, is that if my network is partitioned, then half of my network may see a different transaction added to the ledger, and the other half may get a different transaction added to the ledger. So if the networks are partitioned, so half of the network see transaction T1, half of the network see transaction T2. So in the one half, the first transaction becomes T2. In the other half, the first transaction becomes T1. So there's a divergence. So now there's a question. If you care about availability to make progress, you say, okay, it's okay. I can make the progress and I will figure out later on that there was a consistency issue. But if you say, no, my system is really important about consistency, I don't want to make any decision that may later turn out to cause inconsistencies, then you stop the service. Say, I'm not going to add any transaction unless I know the majority of the replicas on board. So although the CAP theorem suggests that you can pick any two, you can just make sure your system is available of partitioning, or maybe your system can handle both consistency and availability. You can satisfy any possible two. In reality, the kind of in practice, you can't really say that you cannot really choose whether to have full partitioning or not. You cannot really say that I want to be able, I wanted to allow network partitioning, or I don't want it to. It could happen. So partitioning could happen. So there's nothing you can do. So the internet may go down. The router, the switches may go down. There's nothing that you can say, no, I don't want that happen. We can't really make that. It's not a choice. So partitioning, it could happen. So therefore, the only choice that we really have, and the CAP theorem also, I mean, it does prove that, is that assuming that you need to be able to tolerate partitioning, because that's switches could go wrong, machine could go down. So the only thing that you really have a choice is the choice between consistency or availability. Meaning the choice is that you say, okay, I allow my system to progress, so be available, but I sacrifice consistency. Or you say, I cannot sacrifice consistency, so if there is a partitioning, then I will simply let go of the availability. The system will not operate. The system cannot execute any transaction. So again, that's a really fundamental result and observation in distributed system, which has really taken the shape of database company, internet company in the last 20 years. So large distributed system, whether it's by Facebook or Google or any of, especially the social networks or data platforms, it's really shaped by this observation that you really need to kind of choose. And a lot of NoSQL, some of you kind of explored that area. So, but essentially with the NoSQL work, the NoSQL is that they really favor availability. They said, we're going to sacrifice consistency, or we're going to relax our consistency so we can always be available and support partitioning. Traditional databases, it says, we're going to take consistency. So if there is partitioning, then we will sacrifice the liveness. So we will not execute transactions. We're not going to start transferring balances, which we cannot be sure about the correctness of it. So that's the traditional sort of databases that really are strong on consistency, versus NoSQL, very strong on availability. So if you now kind of say, okay, how does the CAP theorem, which is fundamental in distributed system, applies to blockchain? We can see permissionless system, they can tolerate partitioning. It's totally fine if half of the network is down or half of the network is not reachable, as long as in each half the puzzle can still be solved, a block will be added. So partitioning can always be handled, and the system will continue to be available. Of course, there could be forks, and so there could be a consistency issue. So that's the view on the consistency side. The permission setting is slightly more intricate. So the permission setting, it's always about consistency, because if you remember, the problem with consensus was non-divergence and termination. Non-divergence corresponds to consistency. So they do really stress on consistency. And they can only provide availability if the communication is reliable, and they can really be partition tolerance if the network failure is limited to the minority. So as long as as long as the communication is reliable, meaning the messages can be sent eventually, or they arrive eventually, or at least they arrive within some bound, then the system continues to be live and it continues to be available. And as long as only a minority of replicas are affected by partitioning, then they could still tolerate that partitioning, and the system continue to be available as well. Of course, consistency is the prime thing. If consistency cannot be met, the system will stall. The system will not progress. So that's at the corner. So that's a sort of the key property of permissioned setting or traditional consensus protocol. If consistency cannot be guaranteed, the system will indefinitely stall. So any question on this? So again, there's a lot of theory. The most important seminal work is PBFT, developed in 1999, practical Byzantine fault tolerant, that becomes the basis of pretty much any later consensus protocol and the basis of permission setting. So you can always go back to PBFT and look at a variance of that. Very powerful idea. Very simple, but it's also very powerful. So I'm going to go over the PBFT, the concept, the protocol for PBFT. Very simple phases, but to really understand this protocol, which we did cover. So again, all of these slides are kind of, so we had the, I would say the first blockchain textbook, an authoritative source on blockchain, which is published, and these slides are accompanying that book, and you can access it freely as well, as long as you're from the UC Davis campus or log into the library. You can get a free copy of the book as well. So there, we're really focused on the PBFT. Is, I would say, a third of the book is just dedicated to looking in depth and understanding this protocol, which at surface might be very simple, but they simply got it right. There's a lot of intricacy to it, and everything works. So they hit the sweet spot in the protocol. So there's a lot of theoretical study around it. I'm gonna skip that, and so really focus on the PBFT. And it's a primary backup model. Is that in order to orchestrate an election, in order to orchestrate a consensus, in order to orchestrate a voting protocol, we will designate a primary. One of the replica becomes primary or a coordinator, and well, the other one just remain as serving as a replica. And as long as the majority of them are agree on a transaction being added to the ledger, then progress is made. So what does it look like? So for simplicity, we assume the client knows who the primary is and sends the transaction T to the primary. And the symbols around it, the square, the bracket around it, means the request is signed. So the authenticity of the transaction can be verified. So what the primary says, it initiates a phase that calls pre-prepare. And what this prepare does is get that client request and sends it to all replicas. And so it gets the client request and the row number, which is the sequence number. It assigns a sequence number to it, and it tells everyone, this is the transaction I got, and this transaction should be done at sequence number row or sequence number 5, for example. So that's the first phase of PBFT. The second phase, it's called the prepare. In this phase, everybody exchange this message that the primary has sent. So there's a quadratic communication. Everybody sends that message to everybody. And then once the prepare phase passed, there is a phase is called commit. Again, everybody tells everybody that I'm ready to commit. And then eventually, so PBFT has several phases: prepare phase, pre-prepare, prepare, commit, and then informing the client. Now let's start forming an intuition of why do we need any of these phases, or why do we need all of these phases? And it can be proven if you reduce any of these phases, then you can get into very interesting, you can potentially be exposed into different attack model. And so the first one is easy. The pre-prepare, that's a simple one. That's just basically getting a transaction from the client and just informing everybody. So that's simple. Any idea why do we need prepare? Any guess or any intuition that you may have why this phase is needed? Why do we need everybody to tell everybody what they received from the primary? What could be the use of that?
Just to verify maybe there was no data corruption in transmission or anything like that?
So if so assume each message is signed by the client, so the authenticity of the message is there, and you could have a checksum there. And so we can always checksum it. So there's no, we can be sure that there's no corruption in transmission through cryptography and checksum. But you're kind of going toward the right direction. So any thoughts? What if primary, let's say the message is called message M. It tells some replica the next sequence number is message M, and it tells some other replica the next message is message M prime. So the primary could, primary could be malicious, and primary can do anything. So send some client transaction to some replica and send a different client transaction to some other replica and start having a divergence. So what this prepare phase does, it ensures that, and so this prepare phase will only succeed. So once the replica gets a pre-prepare message, they get that proposal message, they all issue a prepare message. And we can say the prepare phase is succeeded if a replica receives from majority of other replica the same message. If each replica observe that the primary did in fact send the message M to the majority, then they can say, okay, the primary is doing the right thing. At least the majority of replica got the exact same thing that I got. It might be the case that a minority never respond. It might be the case the minority never got anything, or it might be the case that the minority got the wrong thing. But as long as the majority is on board on this message that I got as a prepare message, as long as the majority matches, then I can succeed to the prepare phase. Then I can be ensured that the primary sent the same message for the same sequence number to the majority. So that's something that gets established at this point. So here, at this point, the only thing that I knew is that I received the message M. What I know at the prepare phase is that the majority, I know that the majority received message M. So why is it this phase? Why do I need this one? Any thought on this? Again, the pre-prepare phase, I know that I received the message M. Prepare phase, I know the majority have received message M. Why do I need this? What else do I need to know?
We still need to know that the majority have the same ledger after commit, or the same
You're getting there.
Results from the commit, right?
So the commit here is a little bit different from the commit of what we used to. Once we actually reach the commit phase, here is kind of committing on the, we can say the commit here is the transaction was ordered, and at this point it gets executed, and then the client is informed. So the execution may not necessarily even have happened before this point. Yes, the messages are aligned with others. Yes, you're all kind of getting there. So let's kind of go back there once more. At this phase, I know I received message M. At the prepare phase, I know the majority have received message M. But I only know one person who has observed the majority receiving M. Just I'm the only one, as far as I know, I am the only one, or I could be the only one who knows the majority has seen M. but how about the others? At this phase, I know that the majority have seen the majority of them. I know the majority have reached the prepare phase. I know the majority know that the majority have received M. So I'll give you an example, so kind of an analogy. Imagine a classroom. We're all sitting down in a classroom. And one of us is a primary, one of us start texting everybody, okay? So we're all sitting down. If we all get a message from the primary, get the initial text, get the initial pre-prepared text, what we're going to do, so we get an initial pre-prepared text from the primary, and then we're gonna send our prepared text to everybody in the classroom. Okay, so at this point, we're gonna text everybody. We're gonna all text each other. Now at this point, if I receive a text from the majority of the student in the class, I stand. Okay? So whoever stands means it received the majority of the text, who received text from majority of the people. At this point, from an observer, only one person is standing because that one person we know that received the majority of the text. At this point, at the commit phase, we know the majority of the people are standing because the majority of the people have received the text. So at this point, I am certain that no other messages was associated to the sequence number because the honest replica would not accept the same message. The honest replica will not accept two different messages for sequence number, for the same sequence number. So once I reach the prepare state, I can be certain that the primary has not assigned two different sequence number, has not assigned two different messages to the same sequence number. And this one additional phase, I know enough people have observed that. So even if this primary data changes or the protocol needs to restructure, I know that this decision will be remembered forever. So in other words, this phase, I know that the primary hasn't lied or the primary has sufficiently behaved, sufficiently well behaved, meaning the primary send the same, primary has not sent two different messages for the same sequence number. That's why this gets achieved here. And at this point, we can ensure that enough people have observed this message at the same sequence number. And enough people already know that the primary has not assigned two different messages to the same sequence number. And that decision will become permanent. That decision will forever be remembered because enough people have observed it. At this point, only one person, as far as a replica is concerned, a single replica is concerned, only one person, only I know about myself that I know the primary did well with the sequence number. But when I get to the commit phase, I know enough people have seen it. And enough people have reached the same conclusion that I did at the prepare phase. Because the fact that I got a prepare message, the fact that I got the commit messages, meaning that they've also reached the prepare phase. So at this point, I know that enough people have seen that. So if something goes down, something goes wrong, and the primary gets changed, and the primary gets changed, this message will not be forgotten. If a message ever reaches a commit state and the client is informed and the primary does change and we need to restructure and we need to do a leader election, and the leader needs to kind of revisit what was done in the previous round, then anything that was committed will survive. So this is the correctness within the round. This is a correctness across round to remember it. And there's also another thing is that everything is done in a view. A primary operates in a view, and it sequences it sequences transaction within that view. When the primary changes, we go to a new view with a new primary. And the new view has to ensure that everything that was till now was committed, it's also committed in the new view, and so on. So anything that was committed needs to be carried forward. And this commit phase ensures there is enough memory in the network. There was enough messages exchanged in a network that if something was committed, it will be remembered. This prepare phase ensures the primary didn't lie about sequencing the message. The second phase ensures that if the message was correctly prepared by the primary, then it will be remembered. And if enough people have seen it, it will be remembered. If enough people have seen it, enough informed messages will be sent to the client. And if the client gets enough informed messages, meaning enough people have observed it, and if enough people have observed it, meaning that anything that happens later on, the primary changes or the view changes, that message will survive. If you're interested, so this is kind of just give a teaser on this protocol. It's a protocol that really requires, I would say, months to read it and reread it and really look at so many different edge cases that it has in order for it to settle. But it's really very simple, but it's extremely elegant and it's really powerful. It's an extremely powerful protocol. The protocol succeeds at every steps if the majority is on board. If the majority is not on board, the protocol will not succeed and the protocol will stall. And if the protocol stalls, either due because primary was malicious or the network has failed, if the protocol stalls, then it tries to change the primary. It simply just blames the primary for it. And the change of the primary could only happen if, again, sufficient number of replica are on board. So every step of and sort of the elegance of the protocol comes into the simple model that the protocol is able to make a step progression if the majority of the replicas are on board. As soon as the majority of replicas are not on board, the protocol stalls correctly, indefinitely. And yeah, so that's I think any sort of, so is there an intuition for this? I mean, at the face of it is a very simple protocol. Primary gets a message, it tells everybody, and if enough people, and if the primary doesn't lie and everybody gets the same message, or at least the majority got the same message, they all tell each other, well, we got this prepared, we got this message from the primary saying that this is the sequence number for it. If enough people seen it, then they tell the client, we got your message at this sequence number, we executed it, and we informed the client. Very simple at the high level. But the intricacy is sort of in the details. So if the primary is non-faulty and the communication is reliable, I mean, it's possible that the primary is faulty, but some of these lines, these prepare messages are simply not received. None of them could be received, or maybe only one of them is received just because the network is faulty. The network is dropping messages, maliciously or non-maliciously. But as long as the primary is not faulty and then the network is reliable, the communication is reliable, messages not being dropped, and they're delivered in a reasonable amount of time, then the protocol can progress. And what does it mean, reasonable amount of time? Each replica don't know what that network delay is. And as part of changing the primary, they also adjust as necessary. They adjust their expectation of what the network delay is, and they exponentially increase that network delay. If communication is unreliable, they don't get a message from the primary, they try to change the primary, but they're not even able to change the primary, then they all suspect the reason they can't do that because they're expecting the messages to be received within certain time period and they're not receiving it, and that's why they're kind of throwing their hands up. So one way of doing that is, well, they increase their delay, they increase their timeout period. And then they see if now they can change the primary, if they wait longer. And if that doesn't work, they increase it eventually. So they eventually wait longer and longer till the communication is established, the communication becomes reliable, the primary can be changed, and the progress can be resumed. And then they can just go down and reduce their timeout period again. So, but again, there could be Byzantine behavior. For example, primary could get 2 messages from C2 and C1, but it only sends C2 to one replica and C1 to another replica. And the question is, what is it to do? And this is why it's important, is that since we cannot control, usually the number of replica that we have is 3F plus 1. F is the number of faulty that we can tolerate. So 3F plus 1 in this setting, we have N is equal 4. 3F plus 1 is 4. We can tolerate 1 failure. So if our malicious entity is R3, or sorry, if the malicious entity here is actually the primary and the primary sends a faulty message or a different message to some of the replica, still at this phase, as long as the majority can get the correct message, or the majority can agree that they all receive the same message from the primary, as long as the majority can agree, doesn't mean everybody needs to be on board. As long as the majority, which is 2F plus 1 or N minus F, as long as the majority agrees on what the value should be at every phase, then the protocol can succeed. If the majority cannot agree, then it will stall and it will try to change the primary. So in this case, as long as the only thing that has happened, the only malicious thing that the primary is doing is sending a different message to R3, but still, for example, R1 is getting the prepare message for the client message, for the black message from P, R1, and R2. So it's still getting 3 messages. So the progress can be made. But the primary is still also sending its own prepare message and its own commit message. Primary is also a replica. So if the primary then can try to just disrupt the R3. So all the other node can make progress and they will be consistent. In this case, R3 will simply will kind of be it's kind of left behind, and it's okay. We can keep the system can still make progress if one of the nodes are left behind, or minority of the node left behind. As long as the majority is on board on the same value, then the progress can be made. And so that's a resiliency. That's how many fault can be tolerated. So again, primary is faulty. It's another attack model. Primary is faulty. Is basically don't send any message to R3. And so protocol can still continue, but now we have one node in dark. But as long as they still get sufficient number of support for prepare and sufficient number of message for commit, the protocol can continue. And at this point, the R3 can raise its hand and raise a flag saying, I'm not getting any messages, so what's happening? But since R3 is only a minority, R3 cannot trigger a view change, cannot trigger a primary replacement. Although R3 is telling the truth here, saying that primary is not sending me anything, even assuming the network was reliable, because if the network is unreliable, it might be that primary did send it, it just the message was never arrived. but assume the network was reliable, the primary just simply didn't send, R3 on its own does not have enough support to flip the protocol because the protocol is still making a progress. But more similarly, it's possible that the primary did in fact send a message to R3, but R3 was the one who was malicious. And R3 is just told everybody, I'm not getting any messages from the primary. So in fact, from the perspective of R1 and R2, these two cases are identical. When R3 says, I haven't received anything, it might be the case that R3 is lying, or it might be the case that the primary never sent anything to R3. So as long as R1 and R2 are concerned, they cannot distinguish between these two different cases. Therefore, R1 and R2 will only listen to these flags if it comes from enough people. Or in other words, as long as they can ensure that at least one honest replica is raising a flag about the primary, then they will take their word for it, and then try to replace the primary. How do we ensure that? Can you think about how do we ensure that at least one honest replica is telling the truth here? How do we ensure that one honest replica is telling the truth about, for example, primary not sending that message? How can we ensure that? For example, if F+1 replica raise their hand, and we know that there can only be F faulty replica. So if F+1 replica raise their hand saying something is not right, then we know at least one of them is honest. So that we know that then something needs to take a place. But if only in this case, only one single replica is raising their hand, F+1 in this case is 2. So we need at least 2 replica to raise their hand. As long as there's less than 2 replica raising their hand, we can't tell whether they're telling the truth or not, because there could be the one who's malicious. So that's another important point of where to believe replicas when an issue is raised. So as long as the primary behaves faulty to more than F replica, then things could get triggered. So if the primary is clever and it only keeps F replica in dark, then those F replica, if all of them are even good, there's nothing that they can do because they don't have enough support to say that the primary is doing something wrong. We need at least F+1. So in other words, the primary really needs to disrupt at least F+1 honest replica or F+1 non-faulty replica for the view change to happen. So an example of the view change, which is most of this protocol, all the intricacy comes into the view change protocol. The view change is essentially the recovery. So we have the protocol can be broken into a normal execution, which is the commitment protocol. And the commitment protocol is essentially that agreement protocol that they agree when the transaction needs to be added to the ledger at what sequence number. Then there's a recovery protocol if something went wrong, whether the primary was faulty or when the network was unreliable. Then a primary replacement takes place, which is the view change. We'll try to go to a new view. We try to go to a new primary. And there's also a third sub protocol, which is checkpointing. And you kind of have checkpointing in databases. So basically checkpointing is that periodically you checkpointings, making sure that what was done before this checkpoint, everybody's on board. So when I do a view change, when I do a recovery, I don't have to worry about what was before that checkpoint, because before that checkpoint, everybody already on board. All I need to do I need to re-examine what was done after the checkpoint. So in this case, two replicas. So the old primary was B, which is also malicious. And now assume R1 and P prime. These are two replica who haven't received anything from the primary. They're both raise a flag. They send a view change message. So they raise their hand. So that's F plus 1, because that's 2. And R2 so far has been getting messages from primary. So R2 wasn't raising the flag. And R2 isn't an honest replica. But if R2 observes that F plus 1 other replica have already raised their hand, then R2 knows that at least one honest replica is complaining. And as soon as R2 notices that at least one honest replica is complaining, R2 will join the effort. R2 will also propose a view change. And the view change happens when the majority are on board. At this point, the majorities are not on board. There's only F plus 1. But once R2 joins the effort, now we have 2F plus 1. Once the majority is reached, that's when things start to happen. Then the view change takes place. And assume the new primary is P prime. And once the primary P prime receives enough view change messages, then now it has the support to become the new primary. And when it has enough support to become the new primary, it sends out a new view message, and that new view message basically shows the proof that it has received new view change message from the majority, and it also says what was the last stable checkpoint, and it also says what are the different messages that was committed in the last view change that wasn't reflected in the checkpoint. And make sure anything that was committed in the last view that is not reflected in the checkpoint, it also gets reevaluated or recommitted. And that's the view change protocol. So I think I kind of so maybe I'll just first pause here. Any question? There's a lot of exciting and interesting thing about this PBFT protocol, and again, we've been doing a lot of work around it. And so if that's something that it interests you and you're interested in the blockchain space, again, reach out to me and I'm more than happy to kind of get you started on that. There's a few more high level slides. Let me finish those so we kind of wrap up this distributed transaction blockchain lecture as well too. So can we improve? One thing is that what Jim was actually asking early on is about whether do we need full replication or partial replication. Full replication, everybody has a copy of the entire ledger. Partial replication is that everybody just have partial view of the data. And so we could have sharding, is that a non-sharded, a fully replicated system, every replica has all the data, or we could have shards, one have European data, one have American data. And then there is coordination as necessary among these shards. So we no longer need to, every transaction no longer need to be observed both in the European and both in the American shard. So only relevant transaction gets replicated. So that's a very exciting area to work with in this area, in the blockchain space. The other one is kind of specialization, is that what if transactions are not just, they're just read-only, for analytics, for machine learning, for visualization, can be also allow to nodes to, or client to just behave as read-only, and in order to support analytics, can we do that at a lower cost as opposed to ensure that they're part of the consensus or they need to participate in the consensus. So kind of specialization for read-only workloads. So that's another interesting area. So again, there's many different areas, but just in the interest of time, those are two interesting directions. And so sharding or geoscale type of consensus, special role specialization. So we kind of look at information coding in this space. How can you do using information theory to reduce the amount of data that needs to be propagated in order to support analytics. So that's a very interesting direction as well. And again, we've been sort of consensus. There's permissioned, permissionless, a lot of interesting stuff happening. How do you do read-only? How do you do cross-blockchain? So what if I want to communicate or I want to execute transaction across blockchain related to the sharding problem too? Lots of interesting problem in that space as well too. And these are some of the work that we've kind of been looking at UC Davis in our lab with all the students, undergraduate and postgraduate. So looking at how do you do weight-free consensus? How do you do concurrent consensus? How do you do geographically or geoscale consensus? Kind of the lesson in order learned or lesson learned, architectural lesson learned in building blockchain. And how do you optimize the consensus itself? Well, we have proof of execution, for example. Can we drop the commit phase of PBFT? Can we do speculative execution? And sort of many interesting sort of direction around that. So these are some of the work that we've done in this space. And again, if you're interested, please let me know. And of course, we have our own blockchain fabric, ResilientDB, which is part of it is already open source. And I encourage you in the past as well to perhaps download it, fork it, kind of look at it, get familiar with how do you build a resilient and scalable distributed system, and which is centered around transactions. Again, if that's an area of interest to you, and if you wish to participate in the research or in the productization or the commercialization aspect of it, again, we're actively looking in those areas as well too. So let me know. I would be more than happy to get you started on that as well. So with that, if happy to answer any questions, and have a wonderful day, and see everybody on Thursday.